Welcome to section 9.2, a large sample test about a population mean. Today, we're diving into one of the most important tools in statistics, using sample data to test claims about population averages. Think about all the bold claims we encounter every day, like the average fortnight session lasts over 4 hours, or the typical college student gets 7 hours of sleep, or this new energy drink boosts your focus by 20%. Are these claims real or just marketing hype? That's what we're here to find out. Using statistical inference, we'll learn how to evaluate whether a sample mean provides strong enough evidence to challenge a claim about a population mean. When our sample size is large enough, we can use the normal distribution to model these situations and decide, is this average for real or is it just noise? By the end of this lesson, you'll not only know how to run the numbers, you'll know how to argue with the data. Whether it's game time, screen time, or class time, you'll be able to tell when an average holds up under scrutiny and when it doesn't. With hypothesis testing for means, we take what we know from a sample and use it to make an informed judgment about a whole population. Let's say you want to know the average caffeine consumption of college students across the United States. You obviously can't survey all of them, but if you randomly sample 40 or 60 or 200 students, you can use that data to make a statistical inference about the whole group. That's the magic of large sample testing. Now, why focus on large samples, say n greater than or equal to 30? Because thanks to the central limit theorem, sample means begin to follow a normal distribution once the sample size gets big enough, even if the population itself is not normally distributed. That lets us use normal-based methods for inference. Even better, if we don't know the population's standard deviation, and let's be honest, we usually don't, we can still move forward using the sample's own standard deviation, S. This flexibility makes large sample hypothesis testing incredibly practical. You'll use this method anytime you want to test claims about a population mean, whether that's average time spent in a game, average GPA in a dorm, average salary in a region, or average screen time for TikTok users. The process is systematic, logical, and gives us a clear path from sample evidence to population level conclusions. When we want to understand a population, like every college student or all Apex Legends players, it's usually impossible to measure everyone. Instead, we take a sample, a smaller group, and use the sample mean, X bar, to estimate the population mean, mu. Now, here's the idea. If the sample is random and representative, then X bar is our best guess at what mu really is. But what if someone already made a claim about the population? Say a developer claims that players spend on average 2 hours a day on Apex Legends. We want to test whether that's still true with fresh data. So we take a sample of 60 players, and guess what? Their average is 2.8 hours a day. That's a pretty big difference. Now we're starting to wonder, is this just random fluctuation? Or is this difference too big to be due to chance? Could this new sample mean suggest that the true population average has actually changed? This is the logic at the heart of hypothesis testing. If the claim about mu is right, our sample mean should be pretty close. But if our sample mean is way off, that gives us a reason to question the claim and maybe reject it. This process gives us a powerful tool to call out false claims, not just in gaming stats, but in health studies, product performance, social trends, and more. Now that we've introduced the logic of hypothesis testing, let's break down how we actually compute our test statistic when testing a population mean using a large sample. The formula we use is this Z formula, X bar minus the population mean, mu naught, over our sample standard deviation, S, divided by the square root of our sample size, N. Here's what each of those symbols mean. The X bar is the sample mean, the average from the group we observed or surveyed. Mu naught is the hypothesized population mean, the number we're testing a claim about. S is the sample standard deviation, how spread out the sample data is. N is the number of observations in our sample. This formula helps us translate the difference between what we observed and what we claimed into a Z-score, a standard unit that tells us how many standard errors away our sample mean is from the claimed population mean. Now, think of it like this. If someone claims the average jump distance in Apex Legends is 100 meters, but our sample of 60 players averages 108 meters with some variability, the Z-score tells us if that 8-meter difference is a fluke or if it's evidence that something is genuinely different. The bigger the absolute value of Z, the more surprising our sample result would be if the null hypothesis were true. That's the heart of hypothesis testing. Are we seeing random variation or a meaningful difference? And remember, this approach works best with large samples, n greater than or equal to 30, which helps ensure the sampling distribution of the mean is approximately normal, even if the population isn't. Once we've calculated our test statistic, our Z-score, the next step is to decide whether it's extreme enough to reject the null hypothesis, H sub 0. But how do we define extreme? That's where the rejection region comes in. The rejection region is determined by two things: the significance level, which we call alpha, and the direction of the test. Let's walk through three common types. The right-tailed test. Lost my pen again. There we go. So this is our right-tailed test. We reject H naught, the null hypothesis, if the Z-score is greater than the critical value alpha, if it's in here. This happens when we're testing whether the mean is greater than a certain value. For example, a claim that Elden Ring players spend more than 5 hours per day in a game. We're looking for unusually high averages. Now, a left-tailed test, we reject H naught if the Z-score is less than the negative Z alpha right here. This is used when testing if the mean is less than a certain value. For example, a rumor that students are sleeping less than 6 hours a night. We want to know if the average is significantly lower. Now, the two-tailed test, we reject the null hypothesis, H naught, if the absolute value of the Z-score is greater than Z sub alpha over 2. So in other words, this is Z sub alpha over 2, and this is Z sub alpha over 2. So that this area is equal to alpha over 2, and this area is equal to alpha over 2. Whereas in a one-tailed test, the whole area is alpha. This test, the two-tailed test, checks for any difference, either higher or lower from the claimed mean. For example, a claim that the average movie runtime is exactly 120 minutes. Any strong deviation, shorter or longer, could cause us to reject. We usually choose alpha equals 0.05 or 0.01, meaning we're willing to take a 5% or 1% risk of rejecting H naught when it's actually true. That's called type 1 error. So the rejection region is like a red zone on the ends of our distribution. If our Z-score falls in that zone, we say this result is too extreme to be chance. we reject the null hypothesis. If it doesn't fall in that zone, we fail to reject. Now that we know the mechanics of calculating a test statistic and setting up rejection regions, let's walk through the full process of performing a hypothesis test step by step. There are 5 essential steps you'll follow each time. First, state your hypotheses. This means clearly writing your null hypothesis H0, the claim that you're testing, and the alternative hypothesis HA, what you suspect might be true instead. For example, H0 could say the average playtime in Elden Rings is still 7 hours, while HA says it's now more than 7. Choose a significance level alpha. This is your risk tolerance, how much evidence you need to reject the null hypothesis. Common choices are 0.05 or 0.01, meaning you're willing to risk a 5% or 1% chance of making a type 1 error, that is, rejecting a true null hypothesis. Think of it like setting the difficulty level for how much proof you need. Then calculate the test statistic. Based on your sample mean, sample size, and standard deviation, compute a z-score. This measures how far your sample result is from what the null hypothesis says should happen, scaled by the standard error. The farther it is from 0, the more surprising your result is under the null hypothesis. Determine your rejection region or p-value. If you're using critical values, you check if the z-statistic falls into the rejection zone. Or if you're using a p-value, probability value, you compare it to alpha to decide whether the result is statistically significant. Then draw your conclusion. This is where you interpret the result. If your result falls in the rejection region or has a p-value below alpha, you reject the null hypothesis. If not, you fail to reject it, meaning you didn't find strong enough evidence to say that the average changed. Let's say a new patch in Elden Ring claims to improve the average player score. You gather sample data from dozens of players before and after the patch. After running your hypothesis test, if the evidence shows a significant increase in scores, you conclude that yes, the patch likely worked. If not, you fail to reject the original claim. Maybe the patch didn't help as much as advertised. This 5-step logic gives you a clear and consistent way to evaluate data-driven claims, whether it's a marketing team pitching a new product or a studio promising gameplay improvements. Let's dive into an example, one that touches on workplace equity. The question is, are male social workers paid more than their female counterparts? We're testing this based on weekly earnings. Suppose that, according to recent data, female social workers earn an average of $670 per week. That's our claimed population mean. Now we gather a random sample of 40 male social workers, and we find that their average weekly earnings are $705, with a sample standard deviation of $102. We're going to test whether those observed difference is statistically significant or just random fluctuation. All right, so step 1, we're going to set up the hypothesis test. So for our hypotheses, the null hypothesis, mu equals 670. This says the average weekly pay for male social workers is the same as that for females, $670. Our alternative hypothesis is that mu is bigger than 670. This says male social workers earn more than that. This is a right-tailed test, meaning when we look at our normal curve, we're looking at an area on the right. All right, now set up the significance level. So we're going to use alpha equals 0.01, which is pretty strict. This means we require strong evidence to reject the null hypothesis. We're allowing only a 1% chance of making a type 1 error. Now calculate the test statistic. We use the Z formula for testing a population mean. So we take our sample data, right? This is X bar, 705, and subtract the mu value, the population value, 670, over our sample standard deviation, S, divided by the square root of N. Plugging in the numbers we have. This is our N. We get about 2.17. All right, now compare to the critical value. From the Z table, the critical value for alpha equals 0.01 in a right-tailed test is Z equals 2.33. So in other words, this Z value right here that marks our rejection region would be 2.33. Now the one we found is 2.17 over here. That's not in the rejection region, right? This is our rejection region, R, and this is our fail to reject region. So since 2.17 is less than 2.33, we fail to reject the null hypothesis. It's not quite, our result that we got is not quite extreme enough to reject the null hypothesis. So, whoops. While we see that the male sample average is higher, the evidence is not strong enough at the 1% level to conclude that male social workers as a group earn significantly more than females. Now, this kind of result is a reminder that even seemingly large differences, like $35 per week, might not be statistically significant if there's enough variation in the data or if our standards for significance are especially rigorous. In the real world, this result would suggest that either we need a larger sample or that we might retest at a higher alpha level, say 0.05, if the consequences of a type 1 error are less severe. Okay, now let's bring hypothesis testing into the world of gaming, specifically Minecraft. Say a game developer claims that mods don't actually increase the amount of time people spend playing Minecraft. That's our starting assumption, our null hypothesis. But now let's say we collect data to test that. Here's what we observe. We take a random sample of 50 players who regularly use mods. Their average playtime is 4.2 hours per day with a sample standard deviation of 1.5 hours. The company's claim, our hypothesized population mean, is 3.8 hours per day. So step one, we're going to set up our hypotheses. Our null hypothesis, mu equals 3.8. This means mods don't change playtime. Our alternative hypothesis, mu is bigger than 3.8. This say mods increase playtime because we're only interested in whether mods increase time. This is a right-tailed test. So again, we're looking at area on the right. Okay, so we're going to calculate the test statistic. We use the formula for the z-test for means. So we're plugging in our 4.2 average minus the established 3.8 over our sample standard deviation 1.5 divided by the square root of our sample size n. We get about 1.89. So this tells us how far our sample mean of 4.2 is from the hypothesized mean in standard error units. Now we're testing at a significance level of alpha equals 0.05. For a right-tail test, we look it up in a textbook table or use technology to find that the critical z value right here would be 1.645. And we got 1.89, so we're right over here. I'll draw up since I don't have much room. 1.89 there, right? On the number line. So that's bigger than 1.645. We're in that rejection region. Remember, this is our rejection region. This is our fail to reject region. That means the data we collected is far enough from the hypothesized value to be considered statistically significant. So we reject the null hypothesis. There's enough evidence at the 5% significance level to conclude that mods really do increase playtime, at least in our sample of players. This kind of analysis is exactly what game developers, streamers, and digital economists care about. If a feature or mod boosts engagement, that's a huge insight for retention and monetization strategies. This type of testing provides real data to support game design decisions. Let's take a closer look at 3 critical terms in hypothesis testing that often trip students up: type 1 error, type 2 error, and the concept of power, and then how these ideas relate to both real-world and statistical decision making. First, we have type 1 error. This happens when we reject the null hypothesis when it's actually true. It's like accusing someone of cheating in Apex Legends because their stats look suspicious, but it turns out that they're just that good. We thought we saw evidence, but we were wrong. We made a false alarm. This kind of error is sometimes called a false positive. Type 2 error is just the opposite. A type 2 error is when we fail to reject the null hypothesis when the alternative is actually true. So imagine a Fortnite patch really is helping players level up faster, but our data doesn't show it strongly enough. We end up missing something real. That's a type 2 error. This is sometimes called a false negative. Now let's look at the 2 tables on this slide. They help ground these ideas in different contexts. The first table is the jury trial analogy. Think of a courtroom. The defendant is assumed innocent. That's our null hypothesis. If the jury finds the person guilty when they're innocent, that's a type 1 error, a false conviction. If they say not guilty when the person actually committed the crime, that's a type 2 error, letting a guilty person go. This legal metaphor really drives home the consequences of statistical decisions. They're about risk and trade-offs, not certainty. Now, the second table is the statistical framing. Rejecting the null hypothesis when the null hypothesis is true is a type 1 error. Not rejecting the null hypothesis when the alternative is true is a type 2 error. This matrix helps clarify what's going on behind the scenes when we run a hypothesis test. Now let's talk about power, one of the most important yet underrated ideas in hypothesis testing. The power of a test is the probability that it correctly detects a false null hypothesis. In other words, it's the probability of not making a type 2 error. So if a new Marvel movie claims to be more popular than the last one, and we actually detect that difference in audience ratings with our test, then our test had good power. Power depends on several factors, especially sample size. Larger samples it gives us more power or a better chance of detecting real effects. Let's wrap up what we've learned in this section and zoom out to see how it all fits together. First, remember that our goal is to estimate something we can't directly observe, the population mean, mu. Since we can't usually measure an entire population, we use a sample. And the best single number estimate we have is the sample mean, x bar. That becomes our starting point, our anchor for inference. Second, when we're working with a large enough sample, typically n is greater than or equal to 30, the central limit theorem kicks in. That means the sampling distribution of the sample mean becomes approximately normal, regardless of the shape of the population distribution. This gives us the green light to use z-scores and standard normal tables to calculate probabilities and make decisions. Third, hypothesis testing gives us a formal decision-making framework. When we test whether a sample mean is significantly different from a claimed population mean, we're asking, is what we observed just random sampling variation, or is it strong enough evidence to suggest something new is going on in the population? Finally, for these kinds of tests, we use a z-test for means under two main conditions. Our sample size is large, n is greater than or equal to 30. We either know the population standard deviation or are okay using the sample standard deviation S as a substitute. This method helps us assess claims, evaluate changes, and make decisions grounded in data, whether we're testing the effectiveness of a new teaching method, a change in user behavior on a streaming platform, or the impact of a new feature in a game like Fortnite or Elden Ring.